So the big takeaway for the Schrodinger equation is the idea of atomic orbitals. So if we take the Schrodinger equation and we plug in the necessary values into the equation, what the Schrodinger equation gives us are these three-dimensional representations of these three-dimensional objects that tell us in statistical probability kinds of ways the likelihood of an electron being in a space as opposed to in a spot. And the reason for that distinction is something called the Heisenberg uncertainty principle. Um, the uncertainty principle basically says that we cannot know precisely the position and the momentum of an object at the same time, a subatomic particle. Uh, and so for electrons, if we know, the more we know about the position of electron, the less we know about where it's going. And the more we know about its momentum, the less we know about where it is. And so the Schrodinger equation and atomic orbitals say, well, we don't really care about where it is exactly. We just know it's going to be in this space. And so the Schrodinger equation comes up with a series of shapes, sets, that discuss and describe places, locations inside of these energy levels where those electrons could be. And the level of certainty with them is in the like 99% range. So let's take a look at each of the orbitals in turn. So s orbitals. S orbitals exist in every single energy level. They are spherical in shape, and because of their spherical nature, there is no three-dimensional orientation differentiation that we need to worry about. So it's not like some of them are pointing in one direction and some are pointing in another direction. They're all the same. They're all the same shape. They all cover all three dimensions of our coordinate plot equally. But what we should know is that our s orbitals, as we go from the first energy level to the second to the third, we should notice that they get bigger and bigger and bigger. And the reason why they get bigger is as our energy level increases, as we increase the energy of the electron, the more likely it is that that electron is going to be further away from the nucleus. Now, that's not to say that it can't be close to the nucleus. It can. Notice that there are no places in here. It's not like we get to a certain spot and say, oh, it's too close. It's too close. But there's a likelihood that it's going to be further away. And so if I look at these all with that vision of 99% confidence, I can say pretty definitively that an electron in the 1s orbital is 99% likely to be in this zone. In a 2s, it's 99% likely to be in that zone. In a 3s, it's 99% likely to be in this zone. P orbitals start in the second energy level and are dumbbell shaped. And there are 3 of them. They're each oriented along one of the Cartesian coordinate axes. So the p sub x orbital is aligned on the x-axis. The p sub y orbital is aligned on the y-axis. The p sub z orbital is aligned on the z-axis. And it's not shown here, but the higher energy levels, we're going to see the same phenomenon, where as you go to the third energy level and the fourth and the fifth, the p orbitals are going to grow and grow and grow with them. Now, one important thing about the p orbitals, it's not shown clearly here, but there is actually a spot at that origin point where all three of the axes meet, where the nucleus is, that is called a node. And anytime we refer to a node, we're talking about a place in our electron cloud or our electron orbitals where there is no chance of finding an electron. And as we get into higher and higher and higher energy levels, the number of nodes in those orbitals actually increases. But we will always find one node in a p orbital in that spot between the two lobes of the dumbbell. There will always be a node in that area.
Okay, so it's only seen on that one. It's not on the first two.
Well, it is there. It's just the way that they're shown.
Oh, okay.
So they're being shown like this. Well, you can't see what's in between them.
Okay.
If I had turned it to where you could see it, the
Then
node would be there as well.
Okay.
So would you say anywhere there's a cross section?
Right.
So yes, and so every p orbital has two of these lobes that make up the dumbbell. And so the space between the two lobes, that's a node. And so it, like I said, it's not easy to see in the first two drawings, but there is one here and one here, right at that origin point, right where all three of the axes cross. Okay, the last type of orbital that we'll talk about in depth are the d orbitals. Now the d orbitals, you'll see it's a little bit easier to see here. There are actually two nodes on these. You can, I'll show them to you here. You can see that there's a node along this line and a node along that line, where none of these cloverleaf lobes are actually touching each other. And so the spaces between the cloverleaf lobes are nodes. And so the common name for the shape is cloverleaf. And you can see that they 4 of the 5 orbitals in this sublevel look like 4-leaf clovers. The 5th one, the DZ squared, is a little bit different. What the DZ squared kind of takes on is it takes over the spots that are kind of missing from the other ones. Now, understand, in each of these sublevels, so the S sublevel was completely spherical, had no orientations because there's only one orbital in that sublevel. The P had three orbitals in the sublevel. But if I added the 3 together, what I would have got is something that is at least somewhat spherical in shape. Where if I take this one plus this one plus this one, you can see that in total, and I apologize for the horrible drawing here, but you can see kind of in total that they add together to something that is almost spherical in the same way that an s orbital is spherical. And d orbitals kind of do the same thing. if I put together the 5 orbitals in this sublevel, I would get something that's roughly spherical in shape that covers the majority of that space that we would find in the 3D level, in the third energy level or the fourth energy level or the fifth energy level, whatever your case may be. So that's, that's kind of what we're working with there. Now, d orbitals, of the 3 different sublevels that we've talked about, d orbitals are the highest in energy, and that's why we only see them in the third energy level and beyond. So this is what the Schrodinger equation gives us. The Schrodinger equation gives us the model that represents these different shapes, and the different shapes that we get come from the solving of the Schrodinger equation for different scenarios. Now, again, instead of using the Schrodinger equation, what most of us tend to do is we tend to look at things more from the perspective of how can we use the results to actually tell us some things useful about the electrons inside of an atom. And so that's where quantum numbers come in. And so with quantum numbers, what we're going to see is that quantum numbers are 4 numbers that can be used to describe electrons inside of a given atom. And each quantum number tells us something different about the atom, or about the electrons themselves. And so there's kind of a hierarchy here that we're going to examine and explore. So I'm actually going to switch to the whiteboard here to show you this. So from that perspective, we can think of the quantum numbers in describing, first of all, the energy level that an electron is sitting in. And so the energy level, which is given by the quantum number n, is also described as the principal quantum number. And the possible values for this quantum number, we start with the first energy level, and we go up in whole number amounts until we either run out of space, or most commonly we think of if we hit infinity, that's when we can say that the electrons actually left the atom. And so the principal quantum number focuses on that energy level. And so this is kind of the most broad information that we can think of when it comes to electrons. What energy level is it in? The second tier of our cake here is the idea of sublevel. And that's given by the quantum number L, which is known more precisely as the angular momentum quantum number. Now, the angular momentum quantum number is dictated by n to a certain degree, in that it cannot be greater than n minus 1. So again, just kind of following through here, if we want to describe an electron, the first thing we do is we describe what energy level it's in. Then we can describe the type of sublevel that it's in. And the sublevel dictates the shape of the orbital. and it follows a very set specific key. The s orbital is given a number of 0. The p orbital is given a number of 1. The d orbital is given a number of 2. The f orbital, which we didn't even talk about because the shapes are pretty complex, is given a number of 3. But there's two things that we have to think about when we look at this particular quantum number. The first is that if we know the shape, we know what this quantum number is. If we don't know the shape, the quantum number can tell us what the shape is, and we furthermore can understand that the shape cannot be, the quantum number itself can't be any bigger than n-1. So that means in the first energy level, the possible orbitals that can exist in that energy level is only one, the 1s. Because in the first energy level, I can only have a sublevel equal to 0, which means I can only have 1s. I can't have 1p because the quantum number for p is bigger than what's allowed in the first energy level. If I go to the second energy level, I have the possibility for 2s, because I can have 2 and 0, but I can also have 2 and 1, which means that 2p is also possible. In the third energy level, I'm going to change my wording here. Possible sublevels in this energy level. In the third energy level, I can have 3 with s, I can have 3 with p, and I can have 3 with d, because d2 is 3 minus 1. So I've got the possibility of 3s, 3p, and 3d. In the fourth energy level, we can have the 4s, 4p, 4d, and 4f. And so you can see as we increase our energy level, we also can increase the number of possible sublevels in there. Again, as we're going away from the nucleus, we're seeing more and more and more and more and more distance, which means we have the possibility for more and more and more sublevels, which means that we can have more and more and more orbitals, more and more and more electrons. So here are the first two quantum numbers. And so the first two quantum numbers help us to describe any given orbital in terms of what sublevel that orbital is in. And so that gives us an idea of dimension, distance from the nucleus, and shape. The third that we would want to look at is orbital orientation, which is m sub L. Now, in orbital orientation, that is something called the magnetic quantum number. And it is dictated by L, meaning that the range of is from negative L to 0 to positive L. And so this tells us the number of orbitals in a sublevel. So the s orbital, since we're going from 0 and that's it, has one orbital in the sublevel. The p orbital, since we can have a value of -1, 0, and +1, that means there are 3 orbitals in that sublevel. D, I have -2, -1, 0, 1, and 2. That means there are 5 orbitals in that sublevel. And then finally F, I've got -3, -2, -1, 0, 1, 2, 3, 7 orbitals in total. And so we can see that as we're going from box to box to box here, we're getting more and more and more specific about the electrons themselves. Now, the thing that we haven't said yet is how many electrons are in a given orbital. And the answer there is 2, because the answer the last quantum number that we would need to look at is something called electron spin. And so that's m sub s. And what we're talking about here is a specific electron in orbital. Now, m sub s is not dictated by anything. It is either +1/2, which is called spin up, or -1/2 and spin down. Those are the only 2 possible values for those quantum numbers. They're either spin up or they're spin down. And so what this tells us then is this gives us ultimately the number of electrons possible per sublevel. So taking our cues from the previous, there's a possibility of 2 electrons in the s sublevel. There's a possibility of 6 electrons in the p sublevel. There's a possibility of 10 electrons in the d sublevel. And there's a possibility of 14 electrons in the f sublevel. And so we're going to use a lot of this information to probably it's most effective when we start looking at electron configurations tomorrow. Any questions about the 4 quantum numbers at this stage?
No.
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 Okay, so let's go back to the PowerPoint here, and let's look at some practice problems here. So what quantum numbers would be used to describe a 5D orbital? Well, okay, let's change this just ever so slightly. To 5D sublevel. If we're describing the 5D sublevel, we have to know that we're looking at 5 and D. And so the fifth energy level would be described by n equals 5. The D sublevel would be described by L is equal to 2, because the number 2 corresponds to the D sublevel. And so probably one of the bigger mistakes that students make is assuming that n equals 1 business always dictates what the quantum number should be for L. And that's not what it is. N minus 1 just tells us the maximum value of L. If we know what the orbital shape is, then we know what that sublevel designation is going to be. So we know that D corresponds to the angular momentum quantum number of 2. That's where the L equals 2 comes from. What values of m sub L are possible for a 4f orbital? This time we are asking appropriately. M sub L does describe orbitals. We just need to know what ones are possible. To know that, we have to know what the designation is. So the first two quantum numbers here would be n equals 4 and L equals 3 for the f orbital. With that in mind, what would be the possible values for m sub L? Well, recall that m sub L is bounded by L. So it goes from negative L through 0 to positive L. So we could have a negative 3 value. We could have a negative 2 value. We could have a negative 1 value. We could have a 0 value, a positive 1, a positive 2, or a positive 3 value. All 7 of those are possible for this because we don't know which one it is that we're talking about. Does that make sense?
Yeah.
Okay, so when you write it, okay, because like on the homework, I guess they wanted us to just pick one, but in reality, it was all these numbers for the ML.
So if it's asking you for a specific one, they'd have to give you more information. They'd have to give you like an orbital chart or something else. If they're asking you what values are possible, all 7 of those values are possible in this case. In the case of the previous one, if we had drilled down to m sub L, there'd be 5 different values possible for that because we'd be going from -2 to +2.
Okay.
So you just got to be real careful about knowing what the question is asking when you get down into that. All right, any other questions?
No.
All right, so one last practice problem here with regard to, and this is a very common kind of quiz exam homework question. I've got 5 different sets of quantum numbers here. Using our rules, can we determine which of these ones are actually real in terms of which ones could possibly be there? and which ones are completely bogus. And so the way that you do that, the way that you approach it, is you start looking for, okay, start with n. Are these values of n possible? And if they're not, then we need to strike it out. So is a value of 1 possible for n?
Yes.
Yes, there's such a thing as a first energy level. There's such a thing as the third energy level. There's such a thing as the second energy level. Is there such a thing as the negative third energy level?
No.
No. So E, we can not worry about that one anymore. Okay, so thus far we're okay. Now let's go to the next one. If I'm in the first energy level, is it possible to have an s orbital? And the answer there is yes. Every energy level has an s orbital. So this one's okay, and D is okay by the same logic. Is it possible to have a d orbital in the third energy level? Again, our limit here is n minus 1. 3 minus 1 is 2, so that's okay. But is it okay here in the second energy level?
No.
The answer is no. So we can cross off this one now as well. Now we go to the next one. Is it possible to have a magnetic quantum number of -1 for an s orbital?
Yes.
No.
No. Remember, we're bounded, it's positive and negative L. So the only possible value for m sub L, if L is 0, is also 0. This has to be 0 if it's going to work. So that one goes away as well. But can we have a -2 if we have a +2? Yes.
Yes.
Can we have a 0 if L is 0? Yes.
Yes.
In fact, 0 is always an option for m sub L. And so then we look at the last one. Is a value of m sub s at +1/2 possible? Yes. -1/2? Yes. So combination B and D are both valid sets of numbers given our rules. A, C, and E were all wrong.
How did you do that last one, the MS one?
Remember, m sub s has only 2 possible values. It's either +1/2 or -1/2.
So is it the opposite of M sub L?
No, no. The values are always either +1/2 or -1/2. It has nothing to do with any of the other quantum numbers.
Okay, so then it just has to be 1/2, either positive or negative.
Yes.
So if it was like -2/3, that would not be allowed, right?
No.
Okay.
And if it's any number other than positive or -1/2, then it can't happen.
Okay.
All right.